Yeah, like I'm not trying to be a grade killer.
Grade
Mr.
killer.
Zill, one day
I'm
can
not
I just
trying
try
to
and get
stop on
a,
your
can I just
grades.
try and get a
No.
pencil in there?
No.
Why?
Do it in the old part of the building.
Why? Those are too
These are new.
I'm not
Hey.
gonna like take the whole house.
All right.
Put it down.
We
Connor.
are continuing
Do
with
it.
relationships between a function f, its derivative f prime. Now its second derivative f double prime. What we are doing today, we led into yesterday, kind of that same process to find where a function is concave up or down and find inflection points using the second derivative, that sign chart. But there is, before we get there, a second derivative test, which I'll talk about more clearly. Second derivative test is actually an alternative way to find a local max or min. The second derivative test is not used to find concavity or inflection points. So we'll go through an example using it.
Are we
So
gonna
this,
have to know that for our quiz? The concavity, like the inflection points?
yes.
Okay. Because
So-
on homework we had that, but then we didn't have to do those.
They're on there tonight, yeah. So I just wanted to review relationships with concavity, what an inflection point is. I know we talked about it yesterday too, and then there's a couple tests on this front side, and then I have a couple examples for us to work through. So for concavity, as a review from the end of chapter 2, so a function or its graph is called concave upward on an interval I if f prime is blank on that interval. So f is concave up if f prime is increasing. And if f prime is increasing, this means f double prime is what? Positive. Okay, and then just as a reminder, concave up has an upward facing U shape. And another thing I want to add to this, we had talked about this a little bit, I know, with a specific question that was on the final. If a function is concave up anywhere along a concave up curve, the tangent line is always below the curve. So if a curve is concave up, in this case, f anywhere along that curve lies above the tangent line. So usually if you're ever trying to prove that a function is above or below its tangent line, your reasoning would be regarding the concavity of the curve. So then just the reverse of that, a function then would be concave downward on I if f prime is decreasing on I, and that would mean f double prime is negative. And then concave downward is a downward facing U shape. And anywhere along a concave downward facing curve, the tangent line is always above the curve, or f is always below the tangent line. Okay, and then inflection point would be defined as what? What is an inflection point?
When f prime is equal to 0. When f prime is equal to 0.
Well, not necessarily when
Double prime.
yes. So when f changes concavity, an inflection point could occur. Well, the candidates for inflection points would be where the second derivative is 0. It doesn't mean, though, that if the second derivative is 0, there is guaranteed to be an inflection point. Just like if f prime is 0, it's not guaranteed it's a local max or min. So ultimately, inflection point, a point where a curve changes concavity. So if you're looking for an inflection point, you would have to show that, yes, the second derivative would be 0, but then on either side of that point, the concavity is actually changing. F double prime is actually changing from positive to negative or negative to positive. It's not staying the same. So what we'll be using to determine concavity of a function is the concavity test based on what we just reviewed above. So if the second derivative is positive, then we know the graph is concave up. So you can make that sign chart with f double prime, test to see if f double prime is positive or negative. If f double prime is negative, the graph is concave downward. And then wherever the changes in concavity are would be the inflection points. I do want to show you, though, an alternative way. So yesterday we looked at how to find local maxes and mins using that increasing, decreasing test with the sign chart of f prime. You can use the second derivative to also help you find local maxes and mins. So it's an alternative way. Ultimately, how you find local maxes and mins is up to you on your quiz on Friday. But there's an alternate method for it. And depending on what information you have, maybe this would be the method you'd have to use. So what this second derivative test says, it says suppose f double prime is continuous near C. The value C here is a value it shows in both parts A and B. You see f prime of C is equal to 0. So when they're talking about C, C is considered a critical value of f. So if you found the first derivative of a function and you found the critical values where the first derivative was equal to 0, that is a possible place where f could have a local max or min. So instead of then making a sign chart, another way you can do it to determine if there's a local max or min is find the second derivative and substitute that c value also into the second derivative. So this says for part A, if the first derivative at c is 0, and the second derivative at C is positive, then f has a local minimum at C. And the reason why, if f prime of C is 0, that means it's a horizontal tangent. If f double prime is positive, f is concave up. And if you're concave up at a horizontal tangent, it must be a local minimum. So that's the reasoning behind why that's true. And then vice versa, if, again, f prime of C is 0 and the second derivative at C is negative, then f would have a local maximum because now the curve would be concave down at that horizontal tangent, which would have to be a maximum. Okay, so I'll show you in the next example, when it asks to find local maxes and mins, I want to apply this test just so you can see how it works. But you can still find local maxes and mins the way we found them yesterday too. It's just if you, for example, were given maybe that f prime of C was 0 and then you were given information about the second derivative, this is something you could use to determine local maxes and mins. All right, so in example 1, we have a function f. And we are going to find the local max and min values. And again, I want to, for this part, it's not, required, but I want to, for this part, show you how to apply the second derivative test we just talked about. And then we're going to find in part B what we didn't do yesterday, find the intervals of concavity and the inflection points, and then use the information we have from parts A and B to sketch the graph of f without just graphing it on our calculators. We can use our calculator to check, but we're going to sketch it without just graphing it on the calculator. All right, so to find the local max and min values using the second derivative test. So it said, first of all, we need to find the values of C that would make the first derivative equal to 0. So the critical values of f where f prime is equal to 0. So we would need to find f prime. And based on f of x, what is f prime? All right, 4x cubed minus 12x squared. So find then where that is equal to 0. So if we set 4x cubed minus 12x squared equal to 0, how do we solve this for x? And you get x minus 3 equals 0. So then So 4x squared equals 0, meaning x would equal 0, or x minus 3 equals 0, meaning x would equal 3. And there isn't anywhere where it doesn't exist, but for the second derivative test, you wouldn't find where it doesn't exist anyway. Specifically, the first derivative has to be 0 at an x value, or a c value in this case. So then rather than creating the sign chart we created yesterday, where we would put these two numbers on the chart, substitute a value in from every interval into f prime, see where it's positive or negative, that's part of the first derivative test. Second derivative test now says to substitute these values into the second derivative. So we would need to find f double prime. So based on f prime, what's f double prime? Okay, so then we're going to substitute both of these into f double prime. So f double prime of 0 is just 0. And then f double prime of 3 is what did you say?
Well, it's 9
56. I got 36.
Yep.
12 times 9 minus
Minus
72.
Oh,
All right, so then here's where you can either make a conclusion from the second derivative test, or perhaps you can't. If you were to look back, I know it's on the front page. So we had, first of all, if f prime of c, these are our two values for c. So if f prime of c is 0, which is the case for both 0 and 3, and then you're looking to see if f double prime is positive or negative at that value. So we can see at 3, the second derivative is positive. So because f prime of 3 is 0 and f double prime of 3 is positive, that means the function is concave up at 3. This shows that at 3 there's a local minimum. So I could say this conclusion by the second derivative test is that f of 3, which I'm going to just calculate that y value right away, substitute it back into f. So negative 27 I'm getting. So f of 3, which is negative 27, is a local min. Bless you. All right, then I have f double prime of 0 is 0, and 0 is not positive or negative. So this is where I'm not saying that the second derivative test is the best test, because this is where it fails you. You cannot make a conclusion based on this. You can't make a conclusion if the second derivative is also 0 at that value. So what you would have to do in this case is, you wouldn't have to set up a sign chart for the whole thing, but you would have to set up a sign chart with f prime just for the x value 0. Plug in a value back into f prime to see, does f prime change from positive to negative, negative to positive, or not change at all? Does it stay positive, stay negative on either side of 0 to determine if it's a local max or min, or neither. Okay, so if I substitute a value into f prime that's less than 0, it's negative, and then it stays negative. So f is decreasing and then still decreasing. So there is not a local max or min at 0. So I'm just going to make a note here. F of 0 is not a local max or min. So again, the second derivative test didn't help us determine that. We had to then go back and check with the first derivative test to see if it truly was a local max or min. Okay, but we could make a conclusion for f of 3. So there is a local min, there are no local maxes for this function f. So when I ask you to determine local max and min values on Friday's quiz in the future, it does not matter to me if you use the method we learned yesterday, just make a sign chart, or if you want to apply the second derivative test. It's up to you. Either way works and would be a legitimate reason. Yes, Ifrit. We substituted it into f prime first to see if f prime was positive or negative, because that told us if f was increasing or decreasing. But once you actually determine if it's a local max or min, then you plug the value back into f to get the y value. For the chart itself, we substituted into f prime. Okay. All right, so then part B, we did not cover this yesterday, but it is a very similar process to determine the intervals of concavity and inflection points of a function. We know that the second derivative is what determines concavity. If the second derivative is positive, f is concave up. Second derivative is negative, f is concave down. So we have the second derivative. I'm just going to rewrite it here. And normally, when you're testing for where a function is increasing or decreasing or local max and min values, you first found where f prime was equal to 0 or didn't exist to get your critical values on your number line. Here, to test where a function is concave up or down and where it has an inflection point, we need to find where f double prime is 0 or doesn't exist. So we're finding critical values of f prime technically, but we're finding where the second derivative is 0 or where it would not exist. So when we set up our sign chart, we know what values to include on there. So setting this equal to 0, 12x squared minus 24x equals 0. So for x, we can factor out a 12x, get x minus 2, and set each equal to 0. So x is 0 or x is 2. So if there's a possible inflection point at 0 and at 2, we would have to test to see if there actually is an inflection point. And then this is a polynomial for f double prime, so it exists everywhere. There's nowhere it doesn't exist. So I then would set up a separate sign chart for f double prime. We're still using it to determine information about f. And I would put my new critical values on there, 0 and 2. And at both of these values, the second derivative is equal to 0. And I now test a value from each interval into f double prime. I'm seeing if in each interval the second derivative is positive or negative. So if I substitute a value less than 0 into f double prime, it will be positive. So that means on that interval, f would be concave up, however you want to show that to yourself. And then between 0 and 2, so if I substituted 1 in, it'll be negative, so f would be concave down. And then greater than 2, positive. So f is back to concave up. So I'm listing intervals of concavity and inflection points. So I would say f is concave up on the interval from negative infinity to 0, union 2 to infinity. I would think so. I don't think they're picky on that. I think they would know if they're, especially if they're asking for concavity, they would know C would be concave up. So concave down on 0 to 2. I guess my response would be if you're really unsure, because I'm not even totally positive, write it out if you're really unsure.
When in doubt, write it out.
Yes. And then inflection points. F has an inflection point
Oh,
at. So here you would have to double check. Even if I didn't ask you where the function was concave up or down, I just asked you for inflection points, and you found that 0 and 2 were the critical values, don't automatically say these are inflection points. Actually check that the concavity is changing between them. So at 0, concavity does change because F double prime changes sign. So F of 0 would be an inflection point, and also F of 2. And we would need to substitute 0 and 2 back into F to actually get those ordered pairs, or those y values. So based on our function F, F of 0 is just 0. F of 2 is negative 16. Okay, are there any questions on part B, the process we did yesterday, but it's with the second derivative instead of the first? All right, and then for C, I know it says use the information from parts A through C. That should be A through B. To sketch the graph of F. Now you can actually put specific points on your sketch because you have the actual coordinates for the local minimum and for the inflection points. So for example, I know at the point 0, 0, this is going to be an inflection point. I'm just going to put IP next to it. So when I'm sketching it, I know that's an inflection point. At 2, negative 16, I have another inflection point. And then at 3, negative 27, I have a local min. So I'm going to maybe scale my y-axis here by 5s. So this is negative 25 here. This is negative 15. So 2, negative 16, that's an inflection point. And then 3, negative 27 is a local min. Okay, and then I try to follow what I came up with. I know I didn't ask here for increasing and decreasing, but you can kind of see, or we, I guess, could be able to tell even, we know from this sign chart we made here, from negative infinity to 0, it's decreasing. After 0, it's still decreasing, and it's going to start increasing after we reach that minimum of 3, since there's only the one minimum. So I do need to make sure I'm following concavity as well. So I'm starting out on negative infinity to 0, I'm concave up and decreasing. I change concavity from 0 to 2, changes to concave down, but it's still decreasing. Changes back to concave up, and I'm decreasing as I reach the min, and I stay concave up and increase. What was that? Oh, you could, yep. To make it more accurate, yes, you could. All right, any questions on that?
Oh, that was a lot of work.
Yep.
That was a lot of work. Oh my God. That was a lot of work.
Just for good measure.
All right,
That was a lot.
here is more work. Okay, so I know we're not going to get all the way through example 2. This is the Well, what I want you to do is look over this example. Guys, I need your attention for especially part A. That's really the main thing I want to be able to do together. So really, some of the practice here is now focusing on reviewing those relationships with concavity and inflection points, but then also you're going to get for a function, the full problem where it says find where the function increases and decreases and find local max and mins from yesterday, and find intervals of concavity and inflection points and sketch the curve from today. So it's putting it all together. But you may or may not also have a part that says find the vertical and horizontal asymptotes if there are any of a function. So I want to review with you how to do this using calculus, not sketching this on your calculator and saying where the vertical and horizontal asymptotes are. So you may remember limits are what tell you whether or not there are vertical and horizontal asymptotes. You use limits to determine this. Okay, horizontal asymptotes. Horizontal asymptotes you find by finding the limit of the function as x approaches positive or negative infinity. And you can determine, I'll just do positive infinity first, you can determine once you found the limit, since you find them the same way, if they would end up being the same limit. It's going to equal what? Why? Okay, so yes, reviewing, I know there was a limit, at least one limit approaching infinity on the final. So remember, when your x is approaching positive or negative infinity, you are dividing everything by the highest power of x in the denominator. So if you FOIL the x minus 1 squared, you're dividing everything by x squared. And what Pinwish is saying, the shortcut to this is because the highest power is in the denominator, this limit when you divide everything by x squared will be 0. So when the highest power of x is in the denominator, that limit as x approaches positive or negative infinity will be 0. So this limit would be the same regardless of if x is approaching positive or negative. You should check both in case they are different, because you could have two different horizontal asymptotes. So this means the line y equals 0, which is just the x-axis, is a horizontal asymptote. Okay, and then how do you determine where there are vertical asymptotes? You what? How do you make an educated guess? Yes, your candidates for vertical asymptotes are where the function would not be defined, where your denominator would be 0. So it's possible here that we would have a vertical asymptote at what x value? At 1. Okay, here's how you check though, because if a function is not defined, it either means there's a vertical asymptote or it means there's just a hole in the graph. Here's how you check. You find the limit as x approaches that number from at least one side. So I usually do from the right side. And if you can show that this limit would approach positive or negative infinity, that means it's a vertical asymptote. If you actually get a number for your limit, in that case it would be if you got 0 over 0 and had to rewrite it, then it would just be a hole in the graph and not an asymptote. So here if we substitute 1 in, we'd get 1 over 0. So we know it's approaching either positive or negative infinity, and the denominator here is always positive because it is squared. So it is positive infinity, but that tells us that x equals 1 is a vertical asymptote. You do not. You just have to show from one side that you're approaching positive or negative, and that proves it's a vertical asymptote. All right, so some problems might have you do that first and then go into what we did yesterday, find where it increases or decreases, find local max and min, and then find intervals of concavity and use it to sketch the graph. So I know we didn't get all the way through this, but we've been through the rest of this process already. Look at the practice to make sure you get it. Ask me questions if you have them.